Hey guys, welcome to brainAttic. So today we have a couple of very challenging questions from digital VLSI domains. So if you already know, digital VLSI is a very important subject, and if you need a job in the VLSI industry, then you have to be very confident and knowledgeable in the topic. So both the questions which I've picked up today have appeared in GATE 2021. Very recent questions, very conceptual, and for 2 marks each. If you know about GATE, then you know that 2 marks questions are the highest denomination questions, so are very important also. The best part about this is that you will find these questions not only in your GATE exams but also in your placement written exams. And sometimes, if you're lucky, you will get it by the interviewers also. So let us begin solving the problem. So in this first question, we have the propagation delay of AND gate, MUX and NOR gate in the circuit are 2 nanoseconds, 1 nanoseconds and 4 nanoseconds respectively. If the inputs P, Q, R, S and T are applied simultaneously and held constant, then what will be the maximum propagation delay at the output? So the circuit is given to us. We have to analyze the maximum propagation delay at the output. In the next question, if you see, the propagation delay of the XOR gate is 3 nanoseconds. The propagation delay of the flip-flops is assumed to be 0. The clock frequency provided to the circuit is 500 MHz. The initial condition of the flip-flop is given as Q2, Q1, Q0 is equal to 111 with D2 is equal to 1. The minimum number of triggering clock edges after which the flip-flop outputs Q2, Q1, Q0 become 100 in integers is. So let us begin solving the problems one by one. So if you want to give the problems a try by yourself, you can definitely give it a try. Otherwise, you can follow for the solution. So let us begin solving the first problem. So we'll start this solving this problem by finding the all the path delays which are there in this circuit. So if you see, this is one of the path delays. This is another path delay, and this is my third path delay. Now, based on the conditions of t, whether t is equal to 0 or t is equal to 1, which is basically governing the mux inputs over here, as you can follow, we'll identify that which is my maximum propagation delay. So we'll write the gate delays of each of the cells inside them. So this is 2, this is 4 units, this is 2, this is 1 unit, this is 2 units, and this is 1 unit. So if we follow the path above, the top path, then the final output delay is 2 plus 1, which is 3 nanoseconds. For the middle path, if you follow, the total delay will be 4 plus 1 plus 2, 7 plus 1, 8 nanoseconds. And for the bottom path, the delay will be 2 plus 1 plus 2 plus 1, 6 nanoseconds. Now, based on the value of t is equal to 0, your output y will appear with the propagation delay of, so when the t value is equal to 0, this is triggered, but here at the final mux, this 0 is taken. So your output will appear at 3 nanoseconds. When t is equal to 1, then your y propagation delay will be, so y will depend on this and will depend on this. So basically this path is getting traced. So we'll count the delay of the lowermost path, and this comes out to be 6 nanoseconds. So since we are asked the maximum propagation delay, so quickly we can answer that 6 nanoseconds is our answer. Now coming to the next question. Very quickly we solved the first problem. Now coming to the second question. The second question, we are given the frequency of the clock, which is 500 megahertz. And we are given the delay of the XOR gate, which is 3 nanoseconds. Now the initial condition is also given to us, which is Q2, Q1 and Q0 are at 1, 1 and 1, and D2 is also at 1. We'll draw the clock pulse for our visualization of the thing. Now, these are the rising edges of the clock pulse. We'll just mark them. These are the rising edges of the clock pulse. So this is at 0 nanoseconds. This pulse is at 2 nanoseconds. This is at 4 nanoseconds. This is at 6 nanoseconds. This one at 8 nanoseconds, and this one at 10 nanoseconds. Now, the 3 nanoseconds OR gate delay will just mark it here. So this is 3 nanoseconds. And from this 4 nanoseconds pulse edge, right, we'll mark the 7 nanoseconds. Now, we'll see the conditions of Q2, Q1 and Q0 at each rising edge of the pulse. So at 0, Q2, Q1, Q0 is 111. At 2 nanoseconds, since the XOR hasn't produced its output yet, Q2, Q1 and Q0 are still at 1. After 3 nanoseconds, at this edge, the values of Q2, Q1 and Q0 change, which becomes 0, 1, 1. And at 6 nanoseconds, the value, since the XOR gate delay is still there, so we are holding the value 0, 1 and 1. At the 8 nanosecond clock pulse, we see the value 0, 0, 1. So if we count the number of clock pulses which have been taken so far, so this is clock 1, this is clock 2, this is clock 3, this is clock 4 and this is clock 5. So therefore total 5 clocks are required, after which the outputs Q2, Q1, Q0 become 100. If you do like this video, please hit the like button, subscribe to our channel, and for more content like this, please follow us. Thank you so much.